Lecture number 16, acid-base reactions. So now we've started classifying these types of chemical reactions we have. We talked about the first type was these precipitation reactions where we're forming a solid. Now we're going to talk about these acid-base reactions where we're going to react an acid and a base. So let's first define what these acids and bases are. We've talked a little bit about how to name acids and bases before, but we haven't really talked much about what they are. So there's a whole bunch of different definitions. We're going to start with what we call the Arrhenius definitions. An Arrhenius acid is a substance that produces H+, or the H3O+, in water. So when we put an acid into water, we get out either H+, or H3O+. Either way, this H+ is just, it's a hydrogen atom without an electron. So if you remember back to what the hydrogen atom is, the hydrogen atom is just has a single proton and a single electron. We take away that electron, then we have a single proton. So we're forming this H+, the H3O+ is just the hydrated form of that. We'll see in a second. An Arrhenius base is the substance that produces OH- in water, the hydroxide ion. So if we look down here, in this example we have, or I guess on here we have examples of those different acids and bases. So we can look up on top, we have HCl reacting with water to form the H3O+ and the Cl-. On the bottom here we have ammonia NH3 reacting with water to form ammonium NH4+ plus a hydroxide ion, this OH-. So under this Arrhenius definition, if we form H+ or H3O+ in water, then we are getting, that's an acid. If we form the OH- in water, that is a base. Look a minute about this hydronium ion, this H3O+. It's just a hydrated proton, so it's a water that has an additional proton on it or hydrogen on it. That's all it is. It's still pretty much water. It's just the way we show this H+ in solution if we want to be more specific. So we can show it either way, either as an H+ or as this H3O+. Typically I will show it as the H3O+ just to be consistent, but they're equivalent reactions. A little bit different definition, or broader definition, is this Bronsted-Lowry definition. On here it's just Bronsted, but it's Bronsted-Lowry both credited for this. We define an acid as a proton donor. So something that is donating a hydrogen. Right? Since that we take that H+, that is just a simple proton. When we transfer that, that is a Bronsted-Lowry acid. So again, the base then is going to be the one that accepts that proton or that H+. Right? Notice in this definition, we no longer have to be reacting in water. It's a much broader definition. In the Arrhenius, we actually have to be in water, so we're looking at specific products. The Bronsted-Lowry definitions, we no longer have to be in water to make these sort of distinctions, but most of the time in this class we will be talking about water. So if we look at this reaction here, where we take NH3 plus H2O, water, you'll see that the NH3 is accepting that hydrogen or that proton, so it would be the base, where the water, the H2O, is donating the proton, so that is the acid. Right? So in all of these definitions, these Bronsted-Lowry acids must contain at least one, what we call ionizable proton, one hydrogen that can be lost, that can be donated in the reaction. So then when we're defining these reactions, we're always looking for an acid and a base. They have to be paired. If somebody's donating a proton, somebody else has to be accepting a proton. Right? If we look at the Arrhenius equation, those are still true. We still have an acid as a base, as you can see here. We can have, when we talk about at least one ionizable proton, or one hydrogen, that leads us to this idea that we have different levels. We have these monoprotic acids where we have one hydrogen that can be donated, such as HCl. Again, remember HCl is a strong electrolyte, so it's going to be a strong acid. It's completely dissociate when it goes into water. Same thing with nitric acid. If we look at the bottom one, acetic acid, that is a weak electrolyte, so it's a weak acid, so it doesn't completely dissociate when it goes into water. So some of that acetic acid, that H, stays on that acetate ion stays together as that molecule in solution. We can also have diprotic acids where we have two ionizable hydrogens. One, for example, a good example of that is this sulfuric acid, H2SO4. We can lose one hydrogen. Initially, that would be a strong electrolyte, completely dissociates, so strong acid. The second hydrogen, though, is not. It's a weak electrolyte, so it's a weak acid. Well, doesn't lose it when it doesn't dissociate completely, or at least not automatically. And then we can have triprotic acids as well. Phosphoric acid is an example of that. And we can see here, in this case, all three of those losses of hydrogen or protons are weak. So they're all weak electrolytes. So all of those species can exist in solution at one time. So let's look at a couple examples. So let's identify these as either a Bronsted acid, Bronsted-Lowry acid, Bronsted-Lowry base, or both. If we look at the first one, the HI, we have a if we name this would be hydroiodic acid. Right? So we recognize it as an acid, and you see it is an acid. Right? The next one, this CH3COO minus, that is the acetate ion. Right? Since it's negatively charged, it's capable of accepting a hydrogen to make the acetic acid. So that means if it accepts a hydrogen, then it is a base. Right? Sodium hydroxide, the OH minus, if we go to the Arrhenius definition, now when we put this in water, those two ions are going to break apart and will form OH minus. We can see that when we form OH minus in solution, that is the Arrhenius definition of a base, so this is also a base. If we look at this last one, this H2PO4 minus, right, it can gain a hydrogen to form the phosphoric acid, H3PO4, or it can lose another hydrogen to go to HPO4 2 minus. So it can act as either an acid or a base. So we can see that in this case, that can be both. That's what we call amphoteric. It can either be an acid or it can be a base. Right, so these are the things we're going to be looking at when we look at these reactions. When we classify something as an acid-base reaction, we can further classify that as a neutralization. We're taking an acid and reacting it with a base to form some salt and water. Right? So in all of these neutralization or acid-base reactions, we're going to have both an acid and a base to form some ionic salt and water. When we say salt here, we're not typically meaning sodium chloride, what we typically think of as salt. Salt is just a name for an ionic compound that has a cation other than hydrogen and an anion other than the OH or the O. Right? So we're looking for some ionic species, right, that's not water or another acid. So if we look at this example here where we take HCl, hydrochloric acid, and react that with potassium hydroxide, we see that we recognize HCl as an acid. Right? And it's going to donate its hydrogen to the base, KOH, more specifically the OH part, to give us a salt, KCl, and water. So doing the same sort of process we've done before, if we look at the ionic equation, where we look at those species as they exist in the solution as just ions, we see that we have H plus Cl minus plus K plus OH minus, all of which are aqueous. It's going to react to form K plus Cl minus in the aqueous state, and now this liquid water. Right? So it's no longer ions, it's the full molecule, so we'll leave it together. Right? Which means we can balance a net, or create a net ionic equation, where we take the H plus the OH minus goes to water. Where K and the Cl are both, K plus and Cl minus, are the spectator ions. So we see in these acid-base neutralizations, we're always going to get this same net ionic equation of H plus OH minus goes to H2O. We can have multiple, we can have like two H pluses plus two OHs go to two waters. But we'll always have a net ionic equation where we take H plus OH minus goes to water in these neutralization or acid-base reactions. So that's another way we can then use to classify these reactions. If the net ionic equation gives us this, right, we'll see that that is a neutralization reaction. Right? we can then add this to our idea of this stoichiometry by looking at doing this reaction sort of as a step, and we call that a titration. So in a titration, a solution where we accurately know a concentration is gradually added to another solution that we don't know its concentration, right? Knowing that those two are going to react. We can keep adding this known concentration until we get a complete reaction. Right? When the reaction is complete, we've added as many moles of the known value as we have the unknown. That is what we call the equivalence point. The reaction itself is complete. We've converted both of those starting materials to products. Typically we'll use some sort of an indicator like we've done in lab, or we'll do in lab, where we can see this as a color change. So it's typically a substance that changes color near our equivalence point. Right? So once we get close, that solution is going to change color. So if we look down here in this example, we're going to take a basic solution, say KOH, in our burette, where we know its concentration well. And in the flask, we're going to put this HCl solution we don't know. Right? And we slowly add that. Once we get to the equivalence point, as you can see, this solution changes color. It comes to a light pink color because the indicator has changed its form, right? Because we're now at the equivalence point. So stoichiometrically, we can, if we know the volume of that concentration that we know well, that concentration, volume times the concentration gives us a number of moles. If we know how those two react in a balanced chemical equation, we can then convert to moles of the other one. If we know the volume of that solution we had at the beginning, that unknown solution in the flask, for example, then we can calculate the concentration that's in there. So these titrations are going to allow us to calculate concentrations. So let's actually do one of these problems. What is the volume of 0.155 molar HClO4 solution is needed to neutralize 50 milliliters of the 0.0875 molar sodium hydroxide? Right. So we look at how those are related. That it's for every one HClO4, the chloric acid, we're going to react one sodium hydroxide to form this salt, the sodium chlorate, and the water. So if we do that, we can see that if we start with the volume we had, 50 milliliters, convert that to liters, we get times that by the concentration. Now we get moles of sodium hydroxide. They react in a 1-to-1 relationship, so for every 1 mole of sodium hydroxide, we react it with 1 mole of the chlorate. Divide by the number of moles to get the volume. We see that we end up with 0.0282 liters, or 28.2 milliliters. So using this titration, we can then either figure out how much volume we need to add, or what the concentration is either way, using this stoichiometric relationship.
Dad, I done did it.